So what I want to do is, for part 2 of intermolecular forces, is look at a compound and describe a type of intermolecular forces in there. And oftentimes what I'll ask is the strongest type. And again, the way to remember it, ionic, then hydrogen bonded, then dipole-dipole, then dispersion. So these are the weakest. These are the strongest. So normally when I ask it, ionic is greater than hydrogen bonded, greater than dipole-dipole, greater than dispersion. A couple of things also, if it's an ionic compound, it's going to be ionic forces. Polar, you got two choices, hydrogen bonded or dipole-dipole. For nonpolar, it's always going to be dispersion. So let's look at NABR. So whenever it has a metal in it, it's going to be ionic. And so in this case right here, the strongest type of force, or really the only type of force, is going to be ionic. So you write ionic. So again, just classify it. Ionic compounds, ionic. Simple as that. This is water. So again, if you draw out water, you really don't have to draw if you don't want to, but know there's an OH bond. Whenever it's an OH bond, it's always hydrogen bonded. Hydrogen bond is what gives DNA its structure and how proteins interact and stuff like that. So again, hydrogen bond is very specific. Hydrogen or oxygen, hydrogen and fluorine, or hydrogen and nitrogen. If it's not one of these three, it's not going to be hydrogen bonded. So it's very specific. Hydrogen, fluorine, hydrogen, nitrogen, hydrogen, oxygen. If it has something like a carbon and a hydrogen, that's not hydrogen bonded because it's not an oxygen, fluorine, or nitrogen. In fact, this is actually nonpolar. This is going to be a dispersion type interaction. That's hydrogen bonded. This is actually alcohol. This is actually methanol. This one, let's take a look at this here. If you draw this out, we kind of done this in class. OH bond is the strongest. This right here this is negative and positive. This is hydrogen bonded. So that's the strongest type of interactions. There's other types in there. Carbon-oxygen bond. So this is positive and negative. This right here is actually a dipole-dipole. If I just kind of write this down. Carbon-oxygen bond, even like a carbonyl group or carbon-oxygen, that's dipole-dipole. And then carbon-hydrogen is nonpolar. So that's a dispersion. So this one has all three types of interactions. The most important one is going to be the OH. Whenever you see an OH, write on hydrogen bonded. Let's continue. A few things here. So Cl2, and again, it's just two chlorines. You don't have to draw out the Lewis structure if you don't want to. It's just two chlorines. It's going to be a nonpolar molecule, so it's just going to be dispersion. So again, in this case, it's just dispersion. So nonpolar molecule, just dispersion. One thing also, I didn't throw this in there. If I have carbon dioxide, this is a nonpolar molecule. So again, this is one of those examples. Nonpolar molecule, even though it has polar bonds, because these cancel out. So just to kind of know that these dipoles cancel out. This one will be dispersion. CH3, this is actually ethane. This is going to be dispersion. It just has, like, if you draw it out here, just has carbon-carbon bond, which is nonpolar, carbon-hydrogen bond, which is nonpolar. So this is just dispersion. So any type of alkanes will be dispersion. So alkanes will just be dispersion. They're nonpolar, carbon-hydrogen bonds are nonpolar overall, just be dispersion forces. CH3, CN is actually acetonitrile. The only thing you really have to remember for this one, I'm going to draw the Stewart structure for you. For a lot of these complicated ones, I'll give you the structure. You have a carbon-nitrogen bond. That's polar. So positive and negative. So it's going to be dipole-dipole. You have some carbon-hydrogen bonds, which is nonpolar, that's dispersion too, but they always want the strongest. So you got dipole-dipole, which is the strongest. Also out here, you'll have some dispersion. So just kind of be able to recognize these. Just to kind of finish this up. This right here is actually acetic acid. So this is a carboxylic acid. Notice that fatty acids have a carboxylic acid at the end. A few things about this one. This one right here, OH, is going to be definitely hydrogen bonded. Also, it has a carbon double bond O. That right here is dipole-dipole. So just be able to recognize these. This is dipole-dipole. And then carbon-hydrogen, of course, is just going to be dispersion. So it has all three types. Hydrogen bonded is going to be the strongest. A couple of things I want to talk about. When I talk about fatty acids, they have a large nonpolar end. That's actually kind of out, and then there's a polar end. So they got the carboxylic acid part. That's a polar end. When you have something like this, for fatty acids and for soaps, with a long nonpolar end and a short polar end, they'll call this amphipathic. Let me make sure I got that. It means it has a polar end and nonpolar end. They kind of work together. This is soap. Soaps, the only difference is I make this end ionic. And again, this is an ionic end, nonpolar. Always remember, like dissolves like, so polar dissolves polar, nonpolar dissolves nonpolar. The way soaps work is that it can dissolve both polar and nonpolar compounds because it has an ionic and nonpolar end, and I'll call this amphipathic. So just be able to recognize that it has both in those cases.